Hey kids, welcome to section 2.4, sketching graphs of functions. Today you're going to learn how to use key features of functions to sketch graphs of linear functions and then sketch graphs of nonlinear functions. So we've got a lot of vocab here on the next page that we need to understand in order to be able to graph a function. So first, you can use key features of a function to sketch the graph. All the key features I have described down below in this big table are all super important. You've heard of some, but maybe not all of them. These are things like intercept, symmetry, and behavior, things we've talked about, and then new things, intervals where functions are increasing or decreasing, where they're positive and negative. And so you don't need all of the features, every single little itty bitty piece in order to draw a graph. The appearance of the graph could just be depending on the scale that you use for the axes. And so it's not supposed to be, super accurate, but just a general shape. So first thing, x-intercepts. These are the places where the graph crosses the x-axis. So we're looking at a place where it crosses the x-axis, maybe right here, right here. Oh, that's very squishy. But you're looking for the place where it crosses the x-axis. So if we have a diagonal line crossing the x-axis right there. Well, I guess it's x and y axis. Okay, so y-intercept. Y-intercept is the place where the graph crosses the y-axis. We know those two. We also know end behavior. These are our sentences as x approaches positive infinity and as x approaches negative infinity. The new ones that we're going to talk about today are positive and negative and increasing and decreasing. So positive and negative talks about where the function is according to the x-axis. A function is positive on a portion of its domain where its graph lies above the x-axis. And negative, a function is negative on a portion of its domain where its graph lies below the x-axis. So if we have a picture that looks like this, the positive portions would be the parts on top of the x-axis. So this chunk right here, and then all of this chunk is above the x-axis. If we're looking at the negative, that's all the stuff below the x-axis. So we got this chunk right here is negative, and then this dip right here is considered negative. Then the other two to talk about are increasing and decreasing. As the x values increase, the value of the function increases. So that means as you go left to right, your function is going up. If you are decreasing, then as the x values increase, the value of the function decreases. So now you have something that looks like this. So if we look at this picture right here, we are increasing, we are decreasing, and we are increasing. So you follow the curve. All right, these are all the important things that you'll need in order to graph a linear function. So let's practice. Use the given key features to sketch a linear graph. Okay, first thing, the y-intercept is -7. That means that the graph is going to cross the y-axis at -7. 1, 2, 3, 4, 5, 6, 7. Put a dot. The function is positive for x less than -3. That means for all the x's less than -3, so everything that way to the left, the function is positive. Positive means above the x-axis. So that means from here to the left, everything has to be above the x-axis. Okay, the function is decreasing for all values of x. Decreasing means going down left to right. So the picture's got to go down left to right. And then here we get end behavior. As x approaches positive infinity, f of x approaches negative. That means as my x's get bigger, my y's get smaller, so we're going down. The last sentence, as x approaches negative infinity, f of x approaches positive infinity. So as my x's get smaller, my y's are getting bigger. So being that this is a line, if you can take the point where everything is positive and connect it with the place where everything goes through the y-axis, then you've got your linear function. Y-intercept is at -7. The function is positive or above, less than -3. It's decreasing for all values of x, and it matches your end behavior. All right, letter B, the y-intercept is -3, so let's put a dot. The function is positive, that means above. Positive for all x is greater than 1.5. So that means right here. Can make that be a dot. So everything from this dot to the right is going to be above the x-axis. The function is increasing for all values of x. That means as we go left to right, the function is getting bigger. The domain is -2, less than or equal to x, less than or equal to 3. That means the only portion of the graph that I want to look at is between -2 and +3. The range, so that's your x's, the range, that's your y's, is between -7 and 3. So if I go down here, 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, think of this as the box that you are not allowed to get out of. And so I can connect these dots to form a line, but my picture is going to stop at the edge of the box. There's no arrows because it's not going to continue for forever. The domain and range is very specific. All right, so that's how you sketch linear functions. Let's talk about nonlinear functions. So some of the information can be the same, but there's also some different information because now they're nonlinear. So the additional ones we're going to talk about are continuity. We've talked a little bit about discontinuous versus or discrete versus continuous. Continuity, a function is continuous if it can be graphed with connected lines or connected smooth curves. So basically, as long as everything is in a pretty curve, it's okay. If you have a curve, pick it up and then keep going, that's not okay. Extrema, we've talked about those, maximum and minimum values of a function. So we're talking about maximums being up top and minimums being at the bottom. And then we've talked about symmetry. A function has reflectional symmetry if there is a vertical line that divides the graph of the function into two halves that are mirror images of each other. So vertical line, reflectional symmetry. So sketching the graph of a nonlinear function is similar to sketching the graph of a linear function. First, plot the points based on the known key features of the graph, and then draw the lines or curves to connect these points if it's supposed to be continuous. All right, so let's take a look at some of these. Use the given key features to sketch a nonlinear graph. That means I am not going to have a straight line, but some other random wicked shape. All right, so letter A, the y-intercept is -5. So 1, 2, 3, 4, -5, put a dot. All right, the function is continuous. That means there's no breaks or gaps, okay? The function is positive for all x's less than -3 and x is greater than 4. Okay, so that means at -3 on the x's, we're supposed to be positive to the left. And at 4, we're supposed to be positive. So I'm just going to put like little arrows here to remind myself that I'm supposed to be going up. That means in between, we're probably going to be negative, somewhere down below the x-axis. Okay, the function has a minimum at 2, -6. So at 2, -6, this is the lowest point in my graph. Okay, let's see. The function is increasing for all x's greater than 2. So here's 2, the function is increasing. So that means it's going up like this. Okay, I'm starting to think it's going to be like a parabola or something. Let's see, last bit, as x approaches positive infinity, f of x approaches positive infinity. So as x gets bigger, y gets bigger, so going up here like this. As x approaches negative infinity, f of x approaches positive infinity. So So as x's get smaller, y's go up. Yep, so it's going to be some kind of parabola. So let's see, from this point up, we're going to go like this. Now remember, it's non-linear, so your graph should not look exactly like my graph. But there are certain things that you have to make sure you hit. Like make sure that you hit a y-intercept at -5. Make sure you have a minimum, a lowest point of 2, -6. Make sure that you're increasing after 2. Make sure that you're positive after 4. So there are some things to be very careful of. Okay, letter B. The function is continuous, meaning no gaps or breaks, and symmetric about the line x equals -1. Okay, we need to do that first. So we're going to find the line x equals -1, which is a vertical line through the x-axis at -1. This is my symmetry line. So this symmetric part right here is the dashed part that we just drew. That means whatever's on the right side is going to match whatever's on the left side. All right, let's keep reading. The function has a maximum at -1, 4. So at -1, 4, this is the highest point in our graph. As x is as x approaches positive infinity, f of x approaches negative infinity, so we're going to be going down. And as x approaches negative infinity, f of x approaches negative infinity, so we're going down. Okay, now we have to be very careful. We're almost ready. Since the function is symmetric, I need to show the symmetry by picking a random dot on one side of the dash line and reflecting it appropriately to the other side. So pick a dot, I don't know, pick 0, 0. Now, reflect it to the other side of the line to show another dot that the picture goes through. You could have picked any dot in the world. You could have picked a dot way over here, and then your matching dot would have been way over here somewhere. So now to show that it's symmetric, you need to show that whatever you graph on one side of the symmetric line is what's graphed on the other side. I chose to connect them with straight lines. You can also connect them with curved lines. So you could have also drawn it like a curve or with straight lines, absolute value. All right, let's do some more examples. In letter C, the y-intercept is 2, so that means go up 2, put a dot. The function is negative, that means below the x-axis. For x is less than -1 and x is greater than 4. So x is less than -1, it's below. And x is greater than 4, it's below. The function has a maximum at 3, 3. So 1, 2, 3, 1, 2, 3. Okay, so we needed to go through these two dots. It doesn't say anything about symmetric. And then once it hits there, it's got to be below. So let's connect it like this. And, ooh, that was kind of ugly. Okay, let's do, what do we say? 1, 2, 3, 4. I don't know. Let's go straight this way. It doesn't have to be the same on either side. So you can totally make it curved on one side and straighter on the other side. All right, letter D, the function is symmetric about the line x equals 2. So that means find 2 on the x-axis. Okay, symmetric. So I got to show right and left side. The function has a minimum and an x-intercept at x equals 2. So at x equals 2 is an x-intercept, and it's also a minimum. So that means it's either going to curve up or V up. So this point is two things, an intercept and a minimum. End behavior as x approaches positive infinity, f of x approaches positive infinity. So going up, as x approaches negative infinity, f of x approaches positive infinity. So going up. So now I need to show symmetry. So I don't know, let's pick this dot right here. So figure out how far away you are. 1, 2, 3, 4, 5 away. So 1, 2, 3, 4, 5 away. 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 Let's make this one with a curve. So, oh, that's ugly. Wow. Okay, let's pretend that they're symmetric. Okay. So as you can see, you want to try to make it as beautiful as possible. All right, let's do some word problems. So now you're going to have like a story and you're going to have to graph it and kind of try to illustrate it. All right, use the given key features to sketch a nonlinear graph. So not going to be lines in this one. Kenesha follows a walking tour for 18 minutes. The y-intercept Kenesha starts at 0 miles per hour. Is it linear or nonlinear? The function that models this situation is nonlinear. Extrema, Kenesha's maximum speed is 2 miles per hour, which she reaches at 1 minute. She maintains that speed for the next 15 minutes, and then decreasing for the last 2 minutes, Kenesha slows down at a constant rate until she comes to a stop. Okay, so she's on a walking tour. She walks, she slows down, she speeds up, she stops. Along the x-axis is always your time, and on the y-axis is whatever else you are measuring, which is, what are we talking about? Speed. Now it says that her tour is 18 minutes long. That means I need my x's to go to at least 18, which in our case it goes to 20. So we can just kind of label every other if we want to. 2, 4, 6, 8, 10, 12, 14, 16, 18, goes to 20. In terms of speed, it looks like we're going 2 miles per hour as our high point. So, I don't know, we can say that this is 1 mile per hour, and that's 2 mile per hour, and that's 3. I guess I could spread it out and make it taller, but it really doesn't matter. Okay, the y-intercept, Kenesha starts at 0 miles per hour. So at time 0, her speed is 0. That makes sense. The function that she models is nonlinear. That's because she's walking fast and then she's slowing down. Kenesha's maximum speed is 2 miles per hour, which she reaches at 1 minute. So at 1 minute, which is right here, she's reaching her maximum speed, which is 2 miles per hour. So I'm going to put a dot that at 1 minute, she has gone 2 miles per hour. She maintains that speed for the next 15 minutes. So if this is minute 1, 15 minutes later is minute 16. So she's going to stay at that same speed until she gets to minute 16. So I'm going to put a dot at minute 16 and 2. Then for the last 2 minutes, which good because we're at minute 16 and we only have to get to minute 18, so that's 2 more minutes. For the last 2 minutes, Kenesha slows down at a constant rate until she comes to a stop. So at 18 minutes, she's at a stop. So all you have to do now is connect them. So she speeds up, she maintains her speed, and then she slows down until she stops. There's Kenesha. Awesome. Okay. Letter B. An elevator rises from the lobby of a building to the 12th floor, which is at a height of 120 feet. It makes no stops along the way. Okay, so our y-intercept, the elevator starts at a height of 0 feet. That makes sense. It starts at the bottom. The function that models the situation is linear. It's going up. It's not going back down again. And increasing, the elevator reaches its maximum height at 120 feet after 6 seconds. Okay, so time is always going to go along your x-axis. It looks like reaches its maximum height at 6 seconds, and since our maximum height is the floor we're going to, then we need 6 seconds along the bottom. So let's count every other, but count it as 1. So 1 and 2 and 3 and 4 and 5 and 6. And our vertical is going to be the height of our elevator. We have to get to 120 feet, so we can count by tens if we want to. So we'll go 20, 40, 60, 80, 100, 120. Also notice, kids, that there's only first quadrants here. That's because you can't have negative time, you can't have negative height, you can't have negative speed. Even if you're running backwards, kids, you're still running at a positive speed. Okay, so the elevator starts at the bottom. So 0 time, it's 0 feet. The situation is linear, okay? And then reaches its maximum height of 120 feet after 6 seconds. So at 6 seconds, we're at 120 feet. Since it rose at a constant rate, it's linear, we're just going to connect the dots. Oh, that is horrible, sorry. Let's try that again. We'll go this way. Beautiful. No arrows because we're not Willy Wonka. We're not going to go through the ceiling. All right, let's take a look at some more examples. Number 4, this graph shows the height of the tide in a harbor as a function of time in one day. So notice this is a 24-hour clock, and we have height in meters, and so the tide is low at 2 meters, and the tide is high at 8 meters, and the tide is low, and the tide is high, and the tide is low. So if you spent any time by the water, like a ocean or anything with tides, you're going to have water come in and get higher, and water go out and get lower. So part A, what is the greatest height and at what time does it occur? So the greatest height is your maximum. That's going to be these 2 points right here. That's going to be at, the greatest height is 8 meters. And what time does it occur? Well, this is a 24-hour clock, so this first one is 6 a.m. And then 18 o'clock is 6 p.m. And then 24:00, that's midnight. And so the times that it occurs is at 6 a.m. and 6 p.m. 6 a.m. and 6 p.m. Okay, letter B, what is the least height and at what times does it occur? So the least height would be 2 meters. And that is going to occur at midnight and noon and midnight and noon. So at 2 times, at 12 a.m. and 12 p.m. How high is the tide at 4 o'clock? So let's see, 4 o'clock to 4 o'clock would be right here. So if we follow up until we get to the graph and then go over till we get to the y-axis, it looks like it's 6 meters. And then when is the tide 4 meters high? So 4 meters high would be right here, and right here, and right here, and right here. So let's see, this looks to be about 2, 4, maybe 3 a.m. Let's see, at 3 a.m. And then let's go to this one. This one is about 9 a.m. And then we keep going. This one's about 3 p.m. And then, oh, the last one, I bet you can guess. Last one's around 9 p.m. So you can use graphs to predict waves in the ocean. Pretty cool. All right, number 5. When placed in an environment with the right temperature, moisture, and food supply, bacteria will grow at an exponential rate. Which graph best represents bacteria growth if the bacteria's food supply is limited? Explain your choice. Okay, well, this first graph looks like as time goes on, the number of bacteria is at a constant rate, and the direction or the problem specified exponential, so it's not A. Letter B is saying that as time goes on, the number of bacteria decreases and then the number of bacteria increases. But it's actually the other way around. It should increase first and then decrease. So this one is not out because this one's kind of like backwards. If you look at graph letter C, you're starting out with so much bacteria in the beginning, and then it grows really fast. The bacteria stay at about the same rate, and then the bacteria slowly start to die. It does say that your food supply is limited, so that means at some point there's not going to be any more bacteria left. That's graph C. All right, kids, that is the end of section 2.4. If you have any questions, please let me know. And as always, keep calm and keep trucking.